everyone, this is Miss Chelsea, and today we'll be discussing empirical and molecular formulas. Our question of the day is, what are some differences between H2O and H2O2? Our standard is still SC3C, which is to use mathematics and computational thinking to apply concepts of the mole and Avogadro's number to conceptualize and calculate percent composition, empirical molecular formulas, mass, moles, and molecules relationships, as well as molar volumes of gases. So, what is an empirical formula? Well, an empirical formula is also known as a skeleton formula. It gives the ratio of elements in a chemical formula. For example, H2O2 would have an empirical formula of HO because the elements in hydrogen peroxide are bonded in a 1-to-1 ratio. The molecular formula, on the other hand, is the true or actual formula, which gives the actual amount of elements in a chemical formula. The molecular formula of hydrogen peroxide is H2O2, and every chemical formula you've encountered up to this point has actually been a molecular formula. You can think of the empirical formula as the ratio of atoms in a molecule. In order to get the empirical formula from the molecular formula, you would simply reduce their coefficients as much as possible to get the simplest ratios. Let's try this. Here are 4 different molecular formulas. I'd like you to find the empirical formula for each. Well, the ratio of nitrogen to hydrogen in NH3 is 1-to-3. That cannot be simplified, so the empirical formula will just be NH3. If you look at sugar, C6H12O6, you see that the ratio is 6 carbons to 12 hydrogens to 6 oxygens. All of these numbers can be divided by 6 to give us a empirical formula of CH2O. CH2O has a ratio of 1-to-2-to-1, and this cannot be simplified, so the empirical formula will also be CH2O. Notice how, although the previous 2 examples had different molecular formulas, they ended up with the same empirical formula. Now, C4H8ON has a ratio of 4 to 8 to 1 to 1. This cannot be simplified. On the other hand, C2H4ON cannot be simplified any further, therefore it is the empirical formula. If we wanted to calculate a molecular formula using the same ratio, we can multiply all of the subscripts by 2 to get C4H8O2N2. So remember, in order to get the molecular formula, you get some multiple of the empirical formula. For example, the empirical formula CH2O could have the molecular formula CH2O, or C2H4O2, or C3H6O3, or C4H8O4, or C5H10O5, or C6H12O6, and keep going. So always multiply all of the subscripts by the same number in order to get the molecular formula. Typically, you would be given the molecular formula's mass and the ratio of the elements in the empirical formula. By putting these 2 pieces of information together, you can calculate the molecular formula. So let's say you have a sample of an unknown chemical made of 40.68% carbon, 5.08% hydrogen, and 54.24% oxygen. What would the empirical formula be? Well, first, let's assume your sample is 100 grams. Then the percentages would simply convert into grams. If you are given grams from the start, we can actually skip this step. Means we have 40.68 grams of carbon, 5.08 grams of hydrogen, and 54.24 grams of oxygen. Now we're going to need to convert our grams into moles. We have 40.68 grams equal to X moles, because that's what we're trying to figure out. We do know from the periodic table that 12.01 grams is 1 mole. So we can set this up as a ratio or proportion. Or we could recognize that anything divided by 1 is the number it starts with, so all we need to do is, say, x equal to 40.68 over 12.01, which is 3.39. And we have 3.39 moles of carbon. We're going to repeat this process for all elements. So hydrogen would be 5.08 divided by 1.008, which is 5.04. And oxygen would be 54.24 divided by 16, which is 3.39. Keep in mind, you can't have anything besides a whole number of atoms. That means we need to divide all of our moles by whichever number was the smallest to get an accurate ratio of one element to another. So our smallest number was 3.39, so we're going to divide all three number of moles by 3.39 to get 1 carbon, 1.49 hydrogens, and 1 oxygen. Notice how the 1.49 is really close to 1.5. We can double 1.5 in order to get a whole number. So let's double all of our numbers to get a ratio of 2 carbons to 3 hydrogens to 2 oxygens. That means our total empirical formula is C2H3O2. Now let's look at molecular formulas. Let's say you have a sample of an unknown chemical made of 84.31% carbon, 11.53% hydrogen, and 4.16% oxygen. It has a molar mass of 769.24 grams per mole. What would the molecular formula be? Well, if we assume our sample is 100 grams, then those percentages would simply convert into grams, giving us 84.31 grams of carbon, 11.53 grams of hydrogen, and 4.16 grams of oxygen. We can then convert our grams into moles. So carbon would be 84.31 divided by 12.01, which is 7.02. Hydrogen would be 11.53 divided by 1.008, which is 11.44. And oxygen would be 4.16 divided by 16.00, which is 0.26. Since we know we can't have anything besides a whole number of atoms, we're going to divide all of our numbers by 0.26, the smallest number. Doing so will give us 27 carbons, 44 hydrogens, and 1 oxygen as our empirical formula. We then calculate the mass of our empirical formula. So let's say we have 27 carbons, 44 hydrogens, and 1 oxygen in our empirical formula. We then multiply each of those numbers by their masses from the periodic table and add them together to get an empirical formula mass of 384.62. Since our question says the molecular formula has a mass of 769.24, we can then divide that by the empirical formula mass to figure out what we need to multiply by, in this case 2. So once we multiply it, we get 54 carbons, 88 hydrogens, and 2 oxygens for a molecular formula of C54H88O2.